Hello, so today we are going to take a look at this problem as part of Leetcode April challenge. Uh, so let's get started. So this, basically we have an array of stones and each position represents the ith stone. And what we are doing is playing a game with these stones where we take each time the two heaviest stones, match them together, and then we have some rules here for what happens if we do that. So we take the two heaviest ones. If their weight is equal, then both are destroyed, so both can be removed from the list. If they are different, then the stone of the smallest weight is destroyed, and so we have remaining just the difference basically, right? So it takes with it the weight of the other one. And at the end of the game, we are guaranteed that at most one stone is left. And the goal of this problem is to return the smallest possible weight of the stone that we have left. And if there is none left, we can just return 0. So that's kind of the problem. If we take a look at some examples here, this is the array. So first we take the two heaviest one, that's 7 and 8. And so this falls under this condition, and so what is remaining is the highest one minus the smallest one. We can also take just the absolute value of the difference, so that's 8 minus 7, that's 1, and so we get this, and remove 7 and 8 and get push 1 into the array. Now the two heaviest stones are 2 and 4, and so we do the same thing. 4 minus 2, that gives us 2, so we push 2 and remove these two here, and now we end up with this. The two heaviest ones again are these two, so 2 minus 1, that's 1, and so we end up with 3 ones. And now from this, we match 1 and 1 together, those are equal, so both are destroyed, and so we end up with just 1. And now we are done. So when we have only 1 left, the game is over, right? There is no other stone to play with, right? So that's kind of the problem. Now let's see how we can solve it. Okay, so how can we solve this problem? So it's actually pretty much in the description of the problem here. So what the problem said is that we need to take the two heaviest stones, right? So each time, basically, you can see that also from the explanation here, each time take the two heaviest stones, right? And then after that, what we need to do is apply the rules here. Okay, apply rules, which means basically if they are equal, then we remove both. If they are different, we remove both, but add back the difference, the absolute value of the difference. And then we take the two heaviest stones again. And so what this tells us is we need the array we need somehow to maintain the sorting order from smallest to biggest, so we can take the biggest value. Okay, so we need to maintain the order. So one approach would be, okay, maybe let's sort the array initially, and each time remove the two biggest ones, apply the rules, add the difference, and then sort again. But then that would mean we do a loop and then we sort each time, so that would be n squared log n, right? Because sorting is n log n, right? And so that's really not ideal. Instead, we can just use a priority queue, right? Priority queue allows us to pop the largest element each time and allows us to push an element, and when we push the element, the order will still be maintained, so we can just use that. Now, this will depend on the language, the implementation, but with Python we have a heap queue library, and then it has just one characteristic, which is that it allows only for extracting the smallest elements. Okay, but what we can do is get around that, and by just inserting smallest element, so we can just insert the elements in like negative order. So basically just add minus x instead of adding x. what this would mean is that if you extract the highest element, if you extract the smallest element in the negative space, then it will be the highest element when it's positive. What I mean by that is -7 is actually smaller than -5, right? But 7 is bigger than 5. So if we have an array, let's say 5, 7, and we add it to a heap Q in this format, -5, -7, then when we extract the minimum, we'll get -7. And so all we need to do is put -7, and now we have the highest element. And so this is a trick often in Python to get an implementation of a max priority queue instead of a min priority queue, which is the default behavior for heap queue. And that's pretty much all there is to it. So the rest is just implementation detail. So let's just write this here. Some space. And what we need to do here is we just create our heap. And so what we can do is just go through the stones and add each. So heap q dot, this is how we add an element. So heap push. In h, we want to add the value, but we want to add it negative so that when we extract the smallest, we can just put minus, and that would be the biggest element in the stones, right, in the array. And so we do that. And now we need to just start executing what the problem statement says. So while we have at least 2 elements, which means while the length of h is bigger than 1, while we can play the game, then we want to extract the 2 largest element, and that's just heap pop, right? That's what allows us to extract, remove. And so that would be x, but we need to put minus because we added minus here so that we can get the original value from the array. So we pass the heap. We do the same thing for y. I'm going to name it y and x just to follow the format that we have here. And now that we have these two, if they are equal, we just need to remove them, right? Because both are destroyed and pop already done that, right? So what we need to do is just handle this case when they are different. And so we can do if x is different than y, then we need to push to the heap the difference, right? But again, we want to push it negative so that we can maintain getting the right order, right? And so that would be just the absolute value of y minus x. And now, at the end here, we are guaranteed to have only 1 element left. That's what, there is at most 1 element left. So maybe it's empty. So what we can do is return h of 0. Or we could also just pop, whichever you prefer. So I prefer h0 here, but we need to do minus again because we inserted it with minus here as well. If there is an element, we can do it with Python if h. Otherwise, we want to return 0. If there are no stones left, we want to return 0. And yeah, that's pretty much it. So let's run this. Okay, we need to pass the heap as well to our push. And let's use more test cases. Submit. And that passes our test cases. The other thing we can do is just make this shorter, make it simpler. Heap Q has this function called heapify, where you can just pass it a list and it will do this for you, essentially, right? But one thing we need to remember is we need the list to be negative. So what we can do is minus x for x in stones here, and then we can just use heapify instead of adding each element ourselves. So heapify h, and that will take care of it. And then one thing here is that since the values are negative, we actually can just pop here without putting the negative here, because, okay, so just to clarify this a little bit more, so we are doing this, right? and y is just minus this, so let me just add this value here. So it's just this minus this, so it's plus. Okay, and since we are taking the absolute value, so this is plus the absolute value, then it doesn't matter where you put each element, and so we actually don't need these minus values here. So what we can do instead is just remove this and then just pass heap q, and this we can just put it in any order since we are taking the absolute value anyway, and so we can just replace the values here. And then we can, the other thing to wonder is, do we actually need these x different than y? If they are equal, then this value would be 0, and we would add 0 to the heap, which is a value that we want here, right? Since the values are negative, the first value would be any other value if there is a non-zero value, right? And so we actually don't need this if case, right? We can just remove it. Again, to reiterate, y is because if we have another value, then it will be negative, so minus 4. So if there is another value, 0 would always not be in the first position. But if there is only 0, that means we destroyed every stone with another one. Then we want to return 0 because that means no stones left, right? And yeah, so that makes it shorter. And this is a really nice trick, is that sometimes you actually don't need the conditionals, and it's good to question that, because if you have less conditions, then less chance of bugs, right? And now I think this should work, so let's run this. Let's submit. And this passes as well. The other solution we can do is, instead of using a heap, we can just use a list, but make sure we insert in a way that maintains the order. So we can use a sorted array or a sorted list, but each time we push, maintain the order. And to do that, maintaining the order without needing to sort, we can use something in Python called insort. We just insert the element in the right position, while maintaining the sorted order, right? So we can actually just use that. So to do that, let's just remove this. We have our stones, so we can just sort them. Or actually, let me just replace it with A so it's quicker to write. So we can sort it first. And now, while A has at least one element, we will pop from A here. Then we need to insert. So bisect.insert here, which means just inserting while maintaining the sorted order. So when insert in A, the same thing we did before, which is pop. We want to insert the absolute value of a pop and then minus a dot pop. So the two largest elements, the difference over the two largest elements. And since we know this is the larger element, we can just remove, because pop will remove from the end. And so we know it's the bigger element, so it's the larger. We don't need the absolute value. And now that we do that, at the end here, we can just return a of 0. And if a, else 0. So let's run this. And we can submit the solution. And that passes as well. Yeah, so that's pretty much it for this problem. Thanks for watching, and see you on the next one. Bye.